For those of you who don't know me, a few non-sci students in the audience, I'm Dan. My office is just down the hall. And there's no posted office hours. You're welcome to find me in my office at any time or email me to set up an appointment. So feel free to stop in whenever you have questions. So our goals for this course are twofold. Our main goal is to combine special relativity and quantum mechanics. And we're going to do that by starting with a classical field theory and canonically quantizing it. That's not the only way we can arrive at quantum field theory. In quantum field theory 2, we'll take a different approach. This method we're going to use is the simplest and has some nice advantages. So we'll see different formalisms throughout the year that are better suited for different calculations. And more specifically, our goal for this course is going to be to calculate observables of interest, namely decay rates and scattering cross-sections. And along the way, we'll learn how to calculate scattering amplitudes at leading order in perturbation theory. So in the first half of this course, we will learn how to calculate these objects in the simplest possible context, which are scalar field theories, whose excitations, the excitation of a scalar field, will be a spin zero particle. And in the second half of the course, when Tibro will take over the lectures, he'll tell you how to incorporate spin. So he'll tell you how to quantize spinor fields and the electromagnetic gauge field. So you can learn how to calculate these objects for spin half and spin 1 particles. And we'll mention and discuss some of the conceptual subtleties and new concepts that come in when we go beyond leading order and perturbation theory. But most of the technical details will be left to QFT2. So beyond leading order, we need to deal with things like renormalization. And in this course, we'll see why that's necessary, but we won't go into too many of the details of how to actually do that in practice. OK. So on a very broad level, that's where we're going. I'll get more specific in a few minutes. But before I do that, I'd just like to elaborate a little bit about why we are starting with a field, classical field theory, and quantizing it instead of, you can imagine another way to approach quantum field theories, starting with single particle quantum mechanics and trying to make it obey special relativity. The approach we're going to take is easier for a number of reasons. And so the first reason is that if we combine special relativity and quantum mechanics, particle number is not going to be conserved. And to see why that's the case, you can imagine we've got a small box, say of size L, with a particle inside. If we make the box smaller and smaller, the uncertainty principle will tell us that there's an uncertainty in the momentum and therefore also an uncertainty in the energy of the particle. And if we make the box small enough, there'll be an uncertainty in the energy. The uncertainty principle tells us the bound on the uncertainty in the energy is given by h bar c over L. And if we make the box small enough, we can make this uncertainty in energy as large as we like. And so if it's small enough so that delta E is greater than 2mc squared, then there's enough uncertainty in the energy to create a pair of particles. So special relativity tells us that energy and mass are the same thing. If it's a small enough box, we can't even be certain how many particles are in the box. So we can create a pair of particles. So any attempt to make, say, the Schrodinger equation for a single particle relativistic is doomed to failure unless you can somehow incorporate particle creation and annihilation. That's particle number non-conservation is very easy to incorporate if, on the other hand, if we start with a classical field, because in quantum field theory, our perspective is going to be that particles are excitations of fields. So a field can have many excitations, and it's very easy and natural to describe particle number non-conservation in quantum field theory. Another reason we start with fields is this answers the question of why identical particles are identical. So if particles are just excitations of a field, then all electrons across the entire universe are excitations of the same electron field. And there's no, it's automatic that the properties of electrons everywhere in space and time are the same. That's something you have to put in by hand. Otherwise, if you didn't start from this perspective. And a third reason that we start from classical fields is to preserve locality. So fields are often introduced in classical physics to prevent action at a distance. For instance, the electromagnetic field can explain the interaction between two electrons locally without introducing action at a distance. And this property is preserved once we quantize the fields. Locality is usually a property we want our physical theories to possess. And this is automatic. We start with a classical field and quantize it. Okay. So I'd just like to give you a brief outline of my half of the course. So we'll spend, I'll be giving the first 7 lectures, then Tibor will take over. Today's lecture is going to be on classical field theory. So we'll recall a few key results from classical field theory that will be useful for us when we quantize the theory, and we'll come up with a classical solution to known as the Klein-Gordon equation, which is a free field theory, which is going to be the first example of a quantum field theory we're going to use, and that classical solution will be useful for us when we quantize it. We'll also discuss Noether's theorem. And then tomorrow, we will quantize the free scalar field. So this is the simplest, basically the simplest possible field theory. It's got no spin, no interactions, and it will allow us to develop some of the tools that we'll need when we study more interesting interacting field theories. Although we'll see there's already some very interesting new things that occur that you may not expect once we quantize the free scalar field. And then we'll spend basically the next 3 lectures learning how to deal with interactions, so we'll spend the first lecture talking about cross-sections and decay rates. So these are what you can actually measure in the laboratory. And we'll relate these cross-sections and decay rates to scattering amplitudes. And then in the 4th lecture, we will discuss what's known as the LSC reduction formula. LSC stands for Lehman, Szymanczyk, and Zimmerman. And what this formula says is it relates scattering amplitudes to basically correlation functions or expectation values of products of fields. And we'll see what that means later. And then in the 5th lecture, we will see how we can actually compute those correlation functions, which we need to compute the scattering amplitudes, which we need to compute the cross sections. And so by the 5th lecture, we will be able to compute cross sections and decay rates in interacting field theories, and we'll do that by relating our interacting field theories to free field theories, which is the subject of tomorrow's lecture. Then we will learn a more efficient pictorial way to basically do in a single lecture what we did before in 3 lectures, and in practice it also saves you a significant amount of time to calculate these cross sections decay rates using Feynman diagrams. And in my final lecture, before I hand you over to Tibra, I'll discuss some of what goes on beyond leading order and perturbation theory. So the leading order and perturbation theory Feynman diagrams are typically what are known as tree diagrams. They look like trees. And we'll see some of what is necessary to go beyond that. So that's where we're going. Any questions so far on the structure of the course? Yes.
How hard will we be waving our hands in the course?
So quantum field theory is a subject without many aspects of quantum field theory don't have firm mathematical basis. For instance, you can win $1 million. One of the Millennium Prizes is just to prove that basically that quantum chromodynamics, the theory of the strong force, exists, more or less. So it's well tested experimentally, but the mathematical background for much of what we're going to do is some of what we're going to do can be well founded, but other parts there's active research going on in the into the mathematics behind this. But I'll try to outline my assumptions and identify where there are gaps in the explanations. But I'm not going to be 100% rigorous. That's not something I can do. So today, we're going to discuss classical field theory. And there'll be two key results we will derive. The first of which is Noether's theorem, which you've seen twice before, I believe, in the relativity course and in the classical mechanics course. I'm going to do it again because it's just that important. I won't spend a lot of time on it, but it is extremely important. And then the other key result we'll talk about is we'll solve the Klein-Gordon equation. So the Klein-Gordon equation is the Klein-Gordon field is the one we're going to quantize tomorrow. That's the name for the free scalar field. So those are the two key results that you should take away. And we won't need a lot of classical field theory. And basically, most of what we're going to need for classical field theory, we can understand through an analogy with classical particle mechanics. So our main object of study in my half of the course will be a scalar field, which I will denote in two different ways, or actually four different ways if you count the blackboard and the typed lecture notes. So when I write a scalar field, its argument will either be just an x with nothing on top of it. This indicates a 4 vector. And in the typed lecture notes, this is italic. Or I'll write it as phi of t and x, or sometimes x and t. I'm probably not going to be consistent with the order, but it should be clear which is which. And the x with a vector symbol over it is a 3 vector. Or in the typed lecture notes or tutorials, this will be bold. And the analogy we're going to make is that classical field is like a set of generalized coordinates from classical particle mechanics. So here, Q is a set of generalized coordinates for particles, and A labels the coordinates. So we could have a bunch of particles in one dimension, or this could label the different coordinates of the particles in different dimensions. But this is just some finite set of generalized coordinates. And the analogy is basically that we can think about x, the position, as like a label, as like this label A. It labels which of the coordinates. So over here, the big difference between particle mechanics is we just have a finite set. And over here, we've got a infinite set that's continuous. But apart from that difference, classical fields will behave just essentially like a set of generalized coordinates. And so you're all familiar with one example of a classical field, which is the gauge potential in electromagnetism, A mu. So that's one example. So A mu has a Lorentz index, mu, so it transforms like a vector, which introduces a number of complications. So we'll stick to scalar fields, which transform trivially under the Lorentz group. Okay, so this is going to be our object of study. And in particle mechanics, One of the most important objects is the action, which we can write as an integral of sum of L QA U dot A. This is not the most general thing we could write, but we're often interested in Lagrangians that just depend on the coordinates and their first derivatives. And the action could depend on all of them, all the coordinates. And if we use this analogy to write the corresponding equation for a field, we get that the action is just the sum over the coordinates here becomes an integral over the positions. And then we've got the Lagrangian density, which depends on the fields and the first derivatives of the fields. Okay. So several comments about this. So first, when in an integral measure, I'll just indicate whether it's a 3-vector or 4-vector by the exponent here. I'm not always going to remember the hats, or the vector symbols and then notes. I think everything is just italic when it's in a measure, but it should be clear from context, or just this number here, whether it's a 3-vector or 4-vector. Secondly, here, so I've got the Lagrangian becomes a Lagrangian density. That's just based on dimensional analysis. These two objects have different units, so we indicate one with the early script. And the second difference between these two is that here we just have a time derivative. Here we have a d mu. And if we want our action to be, or even Lagrangian to be Lorentz invariant, then every time we have a time derivative, we should also have spatial derivatives. So we're not going to be able to construct a Lorentz invariant Lagrangian, which is the only type we're going to be interested in, out of time derivatives without the same number of spatial derivatives. And so if we have an action in particle mechanics, what we're most often interested in doing is finding the equation of motion. And we find the equation of motion by setting the functional derivative of the action with respect to the generalized coordinates equal to 0. And the analogous statement for fields is we do exactly the same thing. We set the functional derivative of the action with respect to the fields equal to 0. And if we do this, in particle mechanics, what we'll end up with is the Euler-Lagrange equation, which takes this form. Or particle mechanics. And again, we can just use the analogy. So the analogous statement for field theory is the derivative of the Lagrangian with respect to the field minus the forward derivative of dl d mu phi has to be equal to 0. And again, all the time derivatives have to become forward derivatives in order for the Lorentz invariance to work. And these are almost the only equations we're going to need. There are two more. So what we're going to do is in the we'll need to find the Hamiltonian and the conjugate momenta. So in when you go from classical mechanics to quantum mechanics, what you do is you take the generalized position and the momenta, and you promote those to operators and impose commutation relations. We're going to do exactly the same thing in field theory. So we need to figure out what the analogs of the momenta and the Hamiltonian are. And we can do that, again, just using our analogy. So for classical particle mechanics, PA is just the derivative of the Lagrangian with respect to Q dot. The analogous statement, probably guess, just the derivative of the Lagrangian here with respect to this one is a phi dot, not a d mu phi. And the Hamiltonian, the sum PA QA dot minus L. On the field theory side, we can write this as the integral of Hamiltonian density, which is the integral phi of x, phi dot of x minus L. Any questions so far? Yes?
Should the Lagrangian of the particle be outside the bracket? I mean, yeah.
Here? Yes. And this should be just a... Thank you. Okay. So our main theory, the main theory we're going to study for this lecture and tomorrow's lecture, the Klein-Gordon theory, which has a Lagrangian of 1/2 d mu phi minus 1/2 m squared phi squared. And throughout this course, I'm going to be using natural units, where I will set constants h bar and c both equal to 1. You can always go back and figure out what the powers of h bar and c should be based on the units of what, by comparing the units you have and the units you want. So for instance, if you've got a distance and you want a time, you can divide by c. So you know there has to be a factor of 1 over c there. And similar dimensional analysis can always restore any units of h bar and c you want. So the units will be left over with, will usually be a mass or an energy, which are the same thing in natural units if c is equal to 1. And I'll also be using the mostly minus signature. So the Minkowski metric will have be +1, -1, -1, -1, which means that we write this Lagrangian out in terms of components. What we've got is 1/2 phi dot squared minus 1/2 times gradient of phi, spatial gradient of phi squared minus 1/2 squared phi squared. Are there any questions on this terms of units or anything else? Okay. So this is our Lagrangian. And we can then find the momentum just by taking the derivative with respect to phi dot. That's rather easy to do. We just get phi is equal to phi dot. And that lets us write the Hamiltonian. I'm often referring to the Lagrangian density as a Lagrangian and Hamiltonian density as a Hamiltonian. It should be clear from context, but if it's not, please ask. It's common. It's common to do so. But. So the Hamiltonian will just be P Q dot minus L. So or pi phi dot minus L. So that's pi squared minus 1/2 pi squared. So we get a plus 1/2 pi squared, and then just flip the sign of all the other terms. And here is our Hamiltonian. Okay. And the last quantity from classical mechanics we'll be interested in is the equation of motion. This Lagrangian only depends on the first derivatives, so we can just use the standard form of the Euler-Lagrange equation here. So what we need to compute is dl d phi minus d mu dl d mu phi. So dl d phi gives us a minus m squared phi. This term gives us a minus d mu. If we take the derivative of Lagrangian with respect to d mu, we get a d mu phi equals 0. And we can pull out a minus sign and just get d mu plus m squared phi equals 0. And we'll come back to this equation near the end of the lecture and solve it. But here we've applied classical field theory, what we'll need, and we're not going to do a lot of classical field theory beyond this. Okay. So the other result from classical field theory that I'd like to discuss, apart from this Klein-Gordon theory, is Noether's theorem. So what Noether's theorem says is for every continuous symmetry, there's a conserved current. J mu, and conserved means the forward divergence of the current is 0. And if we've got a conserved current, then we have a conserved charge. And we can see that in the conserved charge is Q is the integral of the 0th component of the current over all space. And we can see that this charge is conserved by just using the conservation equation of the current. Let's do that. It's a few lines. So the charge is conserved. That means that dq dt is 0. If we just plug in the definition, dq dt is the integral of dj dt, dj0 dt, which, using the conservation equation, is minus the integral of the divergence of J. That's using the conservation equation. But we can convert this volume integral to a surface integral using Gauss's theorem. So we can write this as an integral over the boundary J dot ds, where ds is a normal vector along the boundary. And this is equal to 0 as long as J goes to 0 quickly enough. As x goes to infinity. And the same derivation basically shows us that charge is conserved locally. So if instead of over all space, we just had over some finite volume, this would tell us that the charge that flows, the rate of change of the charge is determined by how much charge flows out of the boundary, how much current flows out of the boundary. Yes?
The universe is infinite and homogeneous. Why would the sources go to 0 at infinity?
It wouldn't necessarily. But in many cases of interest, it does.
Is there why do we assume that usually?
Yeah, typically we're just interested in some local charge distribution, and the amount of charge goes to 0 far away. Okay. We could look at other configurations, but that's the one that's most often interesting. Yes?
What does the Klein-Gordon-Lagrangian describe?
What does it describe? So this is a scalar field that has a, we can think about this. So this is like the kinetic energy. It's got some gradient energy. We can think about these two terms as like the potential energy. So everything besides the time derivatives. So it costs energy to have spatial inhomogeneities in this field. And there's also this quadratic potential term. So when the field the value of the field is displaced from 0 at any point in space that costs energy. So with this, you can think about this as in that way. And the reason we're interested in it is because so we're basically forced to include these gradient terms if we want a Lorentz invariant field theory. But we're interested in this case where we've got a quadratic potential term because this is going to be like a harmonic oscillator. So a harmonic oscillator would have a quadratic potential term, and that's one of the simplest quantum mechanical systems we can look at. In the same way, because of the quadratic nature of the self-interaction, this is going to be one of the simplest quantum field theories we can have. And the analogies with the harmonic oscillator will become hopefully more apparent later. And that's due to this quadratic term. Yeah.
Is there a name for that equation that we have boxed there? Or is this just...
This is known as the Klein-Gordon equation. Other questions? Okay, so let me give you a proof of Noether's theorem. So we say that some variation in the fields is a symmetry, and let's give a name to the variations that are symmetries. Let's say that it's some function y of the fields. So this is a symmetry. If the when we vary the fields in this particular way, the Lagrangian only changes up to a total derivative. So it's total derivative of some function f of the fields. And so note we're not demanding that the Lagrangian is invariant. But if the Lagrangian only changes up to a total derivative, then the equations of motion will be the same. And so if the equations of motion are the same, we'll say that the dynamics are the same, and therefore this variation is a symmetry. Okay, so to prove Noether's theorem, we just basically need to look at the variation in the Lagrangian. Again, we'll just assume that the Lagrangian is only a function of the fields and the first derivatives of the fields. And so then we'll get two terms. We'll get a term dl d phi times the variation of phi. And then we'll also get a term just like dl d mu of phi times the derivative of variation of phi. And we can use the product rule in reverse, or essentially integrating by parts without the integral, to bring this derivative over here. And what we get, this term is fine, get a minus d mu dl du d mu phi times d phi plus, we have to add back in this term. And so if we just use the product rule on this, we get this term and this term. That's all we've done there. And this expression in parentheses should look familiar. And we've seen it a few times already this lecture. For example, over here. This is just the left-hand side of the equation of motion. So this is equal to 0 if the equation of motion is satisfied. Okay. So that tells us the variation in the Lagrangian is this term, d mu, dl, d mu phi. And let's now assume that this variation is a symmetry. Then the variation is y of phi. And if this is a symmetry, then the variation in the Lagrangian is also equal to this total derivative of f. So we can write this as two ways. We can write this, we got by just varying the Lagrangian and applying the equations of motion. And then our assumption is that this is equal to some total derivative like this. And now we've got both sides are total derivatives, so we can read off the so we've shown that the total derivative of something, which we can call the current, is 0, and that something is just dl d mu of phi times ya times y of phi minus d mu f mu phi. This is our current. So not only have we shown that there is a conserved current, but we found an explicit expression for the conserved current. And so the reason I'm going through this again is because, well, you all know that in classical physics, conserved quantities can make solving many problems much easier. Don't have to deal with solving the full equations of motion if you can identify a conserved quantity. In the same way, conserved quantities can make many problems in quantum field theory easier, and they can give you often give you exact results. Usually, in many contexts, all we can do is perturbation theory. I want to put a very big warning sign on this result. So everything we've done so far is classical. We're going to assume, we're going to use this in quantum field theory several times throughout this course. And it's not always true that classically conserved quantities are conserved quantum mechanically.
Should the d mu before the f mu there be there?
No.
Above the
No. Thank you. So this is a classical result. And quantum mechanically, can produce what are known as anomalies. And this is something we will discuss more in QFT3, if any of you take QFT3. Many times it works, but it doesn't always work. We'll be using it throughout this course and QFT2, and we'll for the purposes of this course, we're only going to give you examples where it does work, but just it's a very important result that it does not always work.
What about when you make a fork current that is like conserved off shell, like independent of equations of motion? What about those?
That's right. So that so you've identified a key point in this derivations. We've used the equations of motion. So what you're referring to off shell. So in quantum mechanics, we'll often talk about on shell particles or off shell particles. Basically, the difference between those are on shell particles satisfy the equations of motion. Off shell ones don't. And yes, we can. So when we look at how this can fail, we can see what the problem is. But so even some things are conserved regardless of whether we apply the equation of motion or not. Was there another question?
Do you have like an example of when this would fail?
For example, there's a U1 symmetry in QCD called axial symmetry, which is not, it's conserved classically. You can just apply this. There's a U1 symmetry. We're going to go through an example in a minute of a theory with a U1 symmetry. QCD is an example that also has basically the same U1 symmetry we'll talk about, but it involves fermions. Many of the important examples where this fails involve fermions, in particular chiral fermions, where it's a good symmetry classically, but not quantum mechanically. So let's go through two examples to see how this works. The first example will be translations. This is a space-time symmetry. We're basically going to assume all of our field theories that we're going to look at in this course. Next courses will be Poincare invariant, so they'll have all of those symmetries. And so the translational symmetry is a symmetry where we take coordinates and shift them. So the translation here, I mean four translations in time as well as space. And if we do this kind of transformation, then what we need in order to find the current is how the fields transform and how the Lagrangian transforms. So the fields transform as follows. So if we assume that epsilon is a small parameter, then we can basically just Taylor expand the field to the first order, and we'll get something like this. And the plus sign is because I'll consider active transformations. It's not super important, but you can imagine if I'm sitting at the origin and so is this piece of chalk, if I move in this direction, the chalk is now in the opposite direction compared to my new coordinates are still centered on me. Okay, so the Lagrangian also changes. The Lagrangian is an example of a scalar field, something that doesn't transform. We're assuming it doesn't transform under Lorentz transformations. And neither do scalar fields. So Lagrangian is a scalar field. So it transforms in exactly the same way. And so we can then just read off the conserved current. So our conserved, there'll be 4 of them because we have 4 translations. So our conserved currents will be J mu nu is dl d mu phi c nu phi, because d nu phi is the variation in the field. And for the Lagrangian, so Lagrangian changes up to a total derivative. And it's a total derivative. If you want to get the indices to match up, it should be the total derivative of delta mu nu L. And this conserved current has a special name. It's known as the stress energy tensor. So I've basically pulled off this factor of epsilon for both of these terms. If you're wondering about that, the variation you might identify as this whole thing, and this whole thing would be the derivative of f mu nu. But if this this is conserved for any value of epsilon, then the coefficient of epsilon should also be conserved. And the conserved charges associated with this symmetry are the 4 momenta. Or just the integral of t 0 mu. 4 momenta. Okay. Let's look at a second example. And this example is going to be one we'll return to. It's another example of a free scalar quantum field theory. And this example has, as I just referred to in response to Aurora's question, a U1 symmetry. And so this example is going to involve a complex scalar field, which I'll denote by capital phi. And it's sometimes useful to think of a complex scalar field as 2 real scalar fields. We can either divide this up into its real and imaginary parts, or its magnitude and its phase. So the example we considered before was a real scalar field. The Klein-Gordon field is a real scalar field. And this, we can write down a complex, a Lagrangian for a complex scalar field with a U1 symmetry. If we take the kinetic term to be basically the same as what we had before, without the half, and with a conjugate on one of the terms. And then we can add a potential that's a function of the norm of phi squared. So if we choose this to be a quadratic potential, then we have another example of a free scalar field theory, and we'll come back to this example in future lectures and tutorials. Okay, so this has a U1 symmetry. So unlike our previous example, this is not a space-time symmetry. This is what's known as an internal symmetry. Just we're changing the fields themselves. No reference to space-time. And the symmetry is if we give phi a phase. If we give phi a phase e to the I theta times phi, then phi star will also change. We'll get the opposite phase. And in order to use Noether's theorem, we need to figure out also not only how the fields change, but how the Lagrangian changes. If we look at how the Lagrangian changes, every term has the same number of phi's and phi stars, and so these phases just cancel out. Here we've got e to the minus I theta times e to the plus I theta. And we're assuming here that theta is a constant. It doesn't depend on space-time. That makes it what's known as a global symmetry. And so this implies that L goes down. What we need in order to use the formula for the conserved current in the form that I gave it to you is the infinitesimal version of these transformation laws. So the formula for the current involved the variation of the field. So y was the infinitesimal variation of the field, and f was the whatever total derivative L transform, the variation of L is equal to. We can make these transformation laws infinitesimal, basically just by treating theta as a small parameter. And if we do that, we get that the variation of phi is equal to I theta times phi, and the variation of phi star is minus I theta times phi star, and the variation in the Lagrangian is equal to 0. So then we can apply our formula for J mu. And so we get the usual term. But we need to account for the variation in phi star. So unlike before, we, in a sense, have two fields here. We can think of the phi and phi star as transforming independently, subject to these relations. And if we've got multiple fields, we should modify this equation, and we should basically just sum over the each of the symmetry transformations for the fields. We should sum over A in the case that we've got multiple fields to transform under the same symmetry. And so that means we get an extra term here. And so now we can just plug in our results, and we get J mu is this derivative. We get d mu phi star, and here we get I theta phi, and over here this gives us a minus or plus d mu phi, then times minus I theta phi star. And this is conserved again for any theta. So we can, the coefficient of theta also has to be conserved. So we can write this in a nicer way, and we can pull out the I. Again, if it's the current is conserved, any constant times that current is also conserved. So we can just write this as and the conserved charge associated with this symmetry can have several different interpretations, depending on context. It can be interpreted as electric charge. Tibor will tell you all about how electromagnetism has a UN symmetry, and it can also be interpreted as particle number in other contexts. So. So, and by particle number here, I mean the number of particles minus the number of antiparticles. We'll see that in a few days, we'll see when we come back to this example that this theory has distinct particles and antiparticles. This is a free scalar field theory with, if we take V to be quadratic, with distinct particles and antiparticles. The first example, the Klein-Gordon example we looked at, which had a real scalar field, doesn't have distinct particles and antiparticles. So that'll be one of the big differences between these two theories. Any questions on this? Yes.
We just kind of made up this Lagrangian, right?
That's right.
How do we just pick it?
How do we just pick it?
We're picking it to conserve that quantity, but I mean, like, how do we know that's actually could describe, like, what we see? Does that make sense?
Okay, so that's a good question. Our perspective in this course is we're going to be starting from Lagrangians. I'm not going to motivate them a lot, and we'll see what kind of physics we get. Going the other way is harder. Trying to figure out, design a Lagrangian to explain the physics you see. One way you can do that is if in experiments you notice a conserved quantity, then you know that there has to be a symmetry, and so that can constrain the Lagrangian you write down. So a motivation for this is, suppose you see, I've observed some scalar particles that have electric charge. Okay, then I know that it has to have U1 symmetry, and so we should write down a Lagrangian that has a U1 symmetry. There's other terms you could imagine writing down. For example, I could imagine writing down the square of this term. I'm not going to do that. And that has to do with some of the things we'll talk about in my last lecture. So in order, a full answer to that question, have to postpone some motivation. Other questions? Yes.
Should I be thinking of phi and phi star as sort of two independent degrees of freedom in this?
That's a useful way to think about it. Yes. You should always keep in the back of your mind that they're related, but it's often useful to think about them as independent. Okay, so remember there are two main things I wanted to talk about today. So the first was Noether's theorem, and the second is this Klein-Gordon field. So let's come back to that. And let's solve the Klein-Gordon equation. And this will be useful. We'll use the explicit form of the Klein-Gordon equation that we'll find today, tomorrow, when we actually quantize the theory. And so the simplest way I know of to solve Klein-Gordon equation is to take a spatial Fourier transform. And I'm always going to put my 2 pi's with my momentum integrals throughout the course. This could also be done by doing a 4-dimensional Fourier transform. It's not that much more difficult, but I think this way is slightly simpler, so I'll do it this way. And remember, the Klein-Gordon equation that we were trying to solve, written out in terms of components, is phi dot minus the 3 gradient of phi squared plus m squared phi squared equals 0. And if we plug this equation in here, what we get is phi dot squared. If we take this derivative, we get pull down 2 factors of I k. And so we get a k squared plus m squared by tilde equals 0. Okay, and so this is an equation we can solve by inspection. Basically, the solution should be exponentials. So we can have an exponential e to the I ek, put a minus here, or an exponential e to the I ekt, where ek is the square root of k squared plus m squared. So I'm giving it this name because this is going to turn out to be the energy of our one-particle states with momentum k and mass m. And so both of these are solutions to this equation, and we can also throw in arbitrary time-independent coefficients for each of the terms. That's a general solution to this equation. We're not done yet. The Klein-Gordon field is a real field. For arbitrary choices of A and B, this is not real. So we need to impose a reality condition. And so Klein-Gordon field is real, so phi is equal to phi star. And using our solution, we have that phi star of t and x is equal to the Fourier transform of our solution for conjugate of our solution. And we can rewrite this. We want to compare this to our original ansatz for the solution. One problem in doing so is that the sign in the exponent has changed. But we can do a change of variables by taking k to minus k. And if we do that, so if we want to take k to minus k, the sign will flip, which is good. That's what we want. Get a sign change here, which is fine. It'll give us some relation between A and B of k and A star and B star minus k. What we need to worry about is what happens to the measure. So if we take k to minus k, what happens is we get 3. So for each of the 3 spatial directions, we get a minus sign from flipping the direction of k. But we also change the limits. And if we put the limits back in the original order, we get another 3 minus signs. So the net result is that if we take k to minus k, the measure is unchanged. We get minus signs directly and also indirectly from flapping the limits of integration. So this is equal to d3k over 2 pi cubed e to the I k dot x by tilde star of t and minus k. Okay, so these two expressions are equal if phi of t and k, a tilde of t and k is equal to phi star of t and minus k. And this is our expression for that. So that tells us that a of k e to the minus I e k t plus b of k e to the plus I e k t is equal to a star of minus k e to the plus I e k t plus b star of minus k e to the minus I e k t. And if we compare these expressions, we see that A has to be equal to B star. So both have the exponentials at the minus sign. And B is equal to A star. Those are the same conditions. So we get that B is equal to A. B of K is equal to A star of minus K. That's the condition we need to impose. We want this to be a real scalar field. questions so far?
For the phi transformed
Yes.
T of k needs to be the same as phi not transformed, or should that also be?
That should also have a tilde. Thank you. Okay. So that's our solution. And we could use this to go ahead and quantize scalar field. However, it will be more convenient if instead we do a little bit of work now trying to put this in as Lorentz invariant a form as possible. It will help us later in that it will make the creation and annihilation operators take a Lorentz invariant form or create Lorentz covariant states. So first, let's rewrite what we found. We found that phi of t and x is the integral two pi cubed a of k e to the I k dot x plus skipping ahead. E to the minus I k t plus I a dot x plus a star of minus k e to the I e k t plus I a dot x. Okay. So after we quantize the theory, these A and A star will become the annihilation and creation operators. And so nothing or not much of what this expression right now looks very Lorentz invariant. We've got a three-dimensional measure. Over here, we've got the wrong sign in the exponent to make a 4-vector. So it will save us some work later if we massage this and make it more Lorentz invariant. This term already looks nice. So we've got here different signs between the time and the space components. And so we can write this term here as e to the I k dot x. Remember, without the vector symbol on top, k and x are 4 vectors. And we're identifying here the 0th component of k to be ek. We can write this part in terms of Lorentz invariant. This part, we've got the wrong sign to do that. But we can use the same trick we just used, taking k to minus k to flip the sign of k. So this term, you can take k to minus k. And if we do that, this term is equal to, well, here we get a star of k. The measure won't change, and we'll flip the sign here. So here we'll get a minus sign? Should be a minus sign. Okay. Mostly using the mostly minus signature. So if we do that, here we'll get a e to the I k dot x. So what we get then is tx integral d3k 2 pi cubed a of k e to the minus I k dot x plus a star k e to the I k dot x. And it's looking better. This part looks Lorentz invariant, but we still have the measure. So let's see if we can make the measure Lorentz invariant. And to do that, well, the natural starting point is with a four-dimensional momentum integral. So that should be Lorentz invariant. We're treating space and time the same. But we want to get a three-dimensional momentum integral. So the natural way to try to do that is to throw in a delta. And we want to keep this Lorentz invariant. The argument of the delta should be something Lorentz invariant. Well, over here, we're imposing the condition that k0 is equal to ek. So we have k0 is equal to ek, which if we square this as k0 squared is ek is k squared plus m squared. We can write this as k squared is equal to m squared. So that's the Lorentz invariant. We're already imposing that condition, so we can just impose that condition on our four-dimensional integral in order to do the k0 integral. So that's Lorentz invariant. This doesn't quite work because k squared minus m squared equals 0 has two solutions. K0 squared k0 could be equal to ek. It could also be equal to minus ek. Again, what we're going to interpret ek is as the energy of a one-particle state. We don't want negative energy one-particle states, so we want to get rid of the solution where k0 is equal to minus ek. And the natural way to do that is to throw in a Heaviside function. Okay, so this one looks worrisome. The argument is definitely not Lorentz invariant. But the sign of k naught is all that really matters. And the sign of k naught is not changed as long as we restrict ourselves not to the full Lorentz group, but the orthochronous Lorentz group. This is invariant under the orthochronous Lorentz. And so this integral is equal to, when you use the delta, remember delta of a function, we get an extra factor that's 1 over the derivative of the function. So you get it 1 over 2 ek. We use this to do the k0 integral times the integral d3k over 2 pi cubed. And so we can make this Lorentz invariant by just pulling out a factor of 2 pi. to ek. So if we define a of k to be equal to a small a of k over 2 ek, then we can write phi of t and x is the integral d3k over 2 pi cubed 2ek a of k e to the I k dot x minus plus a star of k e to the I k dot x. And so this is Lorentz invariant, this is Lorentz invariant, these exponentials, this is Lorentz invariant. So it's probably not surprising that the A's have nicer Lorentz transformation properties, the small A's than the big A's. And this, apart from another theorem, is the most important result of today. And we'll use this tomorrow to quantize the scalar field. These A's will become creation and annihilation operators. Any questions? Go ahead.
Is there some kind of physical significance to the fact that we go from a real field to a complex field? Or, can we describe the same physics of a complex field using a real field?
We could describe a physics of a complex field using two real fields. But if we describe it with a single complex field, then the symmetries will be more transparent. So if we write it, I don't know where it went, but that Lagrangian had a U1 symmetry. If we wrote it in terms of two, it was not too hard to see. We could see if we gave everything a phase, it was pretty transparent that we got a Lagrangian that was invariant. If we wrote it in terms of two real fields, it'd have the same symmetries, but it would be less obvious. So the physics would be entirely the same, but it might not be as easy to see. Any other questions? Sam? That comes from this relation that delta of f is the sum I of delta I'll write it like this, xi over f prime of xi. Sorry, in the notation of the front end, I wrote it like this. Or f of xi 0. So this is just saying if we got delta of a function, which we do, our function is k squared minus m squared, then the delta function, we get this extra 1 over the derivative term. We don't just evaluate the delta function or whatever's multiplying the delta function at the zeros. We have to take care of the change of variables, essentially.
Can you say that again?
So the delta you think of as picking out whatever it's being integrated against. If we have integral of something times delta of x dx, you think about the deltas, picks out this thing at 0. If we have delta of f of x, it picks out not just where we have to basically do a change of variables to put it into this form. So it doesn't just pick out the value of the test function at 0. We have these extra factors. Other questions? Okay, I'll see you tomorrow.